I'm going to try to get the test done by around noon on Friday. Are you all able to have the test done before Monday at midnight? Would Friday afternoon, Saturday, Sunday, and Monday be sufficient time? Is there anyone who has a problem with that?
You need more time?
Everybody's good in that time frame? Okay, then that's what it will be. And we'll cover the rest of the stuff today. Okay. Do you have any question about anything we've covered as of now? Class bells rung. Lena, you're not sounding like anything. I hear nothing, but I saw that I have a question. Okay, while Lena's looking at that. Tomorrow's gonna be interesting. Great soundings, but they're big time cap.
They dropped to 10%.
Yeah, that's because capping.
Cap.
But we'll see.
Texas is looking good though. Big time hail, as always.
If it gets thunderstorms. I'm just looking at this. Most likely it will be strong vertical shear, lots of instability. It says, provide support for the risk of severe storm development, though the extent and focus details remain unclear at this present time. So, Kerr, this is not a really good description of what's going on. Well, he just didn't. Yeah, whatever. Sorry, Lena, you working yet? You might need to break out of the room and then come back. Ryan, you got any questions? Isaac?
Not right now.
No.
You know, as long as you keep showing up, that makes me happy. Julia, you got any questions?
Yep. Paul, could you go over the scattering formula again?
Sure thing. Let me do this. Let me do this. Lena, say something. You might need to reboot your computer. Go ahead, reboot the computer. I'm gonna answer a question here, and then we'll talk. Okay, so the scattering, what we're saying here is that the actual formula is this. Now, whenever I've got a constant, you know, if you wanted to, you could rewrite this formula as this. Right? Do you agree this and this are the same?
Yeah.
Okay. In that case, you have A equals B over C. We know that the scattering efficiency, how well something scatters, is directly proportional to this. Now, that's how we do that if K is constant, which we know it is. So whenever you see a formula like this, you're really saying Q sub S is directly proportional to alpha to the fourth. But alpha is a size parameter. It's basically a ratio. It's a comparison. It's a fraction between the size of the scatterer based on the circumference and the wavelength. So there's actually two things I care about. So when it goes right down to it, I'm going to say this is equal to K times 2 pi r all over lambda to the fourth power. Okay, you follow that? Now, given that this is the case, we said we've got 3 variables. We have this, this, and this. A subscript is never a variable. It's just a clarification. I don't like 3 variables. I need to hold one of them constant. So I want to know how well something scatters, and I want to know why the sky's blue, which implies that this and that are variables. The radius does not change. So what I'm saying, and this is the key part, is that this guy is a constant. Well, 2 pi is a constant. And a constant times a constant is just a constant. It's different, but it's still not changing. And a constant taken to the 4th power is just a different constant. And a constant times a constant is just a different constant. So this whole thing simplifies to this. Now, how many variables do I have? 1, 2. Everything on the top is a constant because I said radius is a constant. And therefore, I know that the scattering efficiency is inversely proportional to the wavelength. In other words, shorter wavelengths scatter better. Whenever I say that, that's a comparison. I said, how much better? That's a fraction. And that's what we did the other day. This formula only works for Rayleigh scattering. Right? It's only working for Rayleigh scattering. The other 2 types of scattering, one of them is called Me, and the other one is geometric optics. Right? But geometric optics, I don't need a formula. I just know the angle in equals the angle out. It bounces, it reflects. Me scattering is a very difficult equation. Fortunately for us, we only need to know that it exists. We don't need to worry about how it affects the atmosphere because it doesn't. The atmosphere doesn't have Me scattering, mostly. So Rayleigh scattering is the only one, and that's the equation. Does
Okay.
that help, Aaron?
That help? Yeah.
Good. Lena, how about you? You working yet?
Hear me?
I can hear you really quietly. Are you muted?
Wait, hold on. Can you hear me better now?
I can hear you a little better now.
Weird. Okay, I'll have to figure that out.
Well, go ahead and say it because I can hear you enough to hear you.
Okay, so I was in a Strom class last night, and they're talking about like how they use like red flashlights and like at night because it doesn't leave like the glare. So does that all have to do with like the wavelength of red light versus like a white light flashlight?
Okay, I heard that you used a flashlight in an astronomy class, and you were talking about what works better at night?
Like red light because it doesn't leave a glare. Like, does that have to do with the wavelength?
It might be. I would think that the red light that you use is a little bit less intrusive into your eye, so that when it's dark out, your eye, because what happens when you put light in your eye? This is just a side note. What happens when you put light in your eye? Zach, do you know?
It reflects the back and it like,
Well, no. I mean, what physically happens to your body, your eyes?
oh, you dilate your eyes.
Your eyes not dilate, they get smaller. They
Oh, yeah.
constrict. So the pupil gets smaller. It's like a camera. You're letting in less light because there's so much light. Your optic nerves are going, whoa, that's too much light. So at night, your eyes are dilated really big. If you use red light, I would assume that it may have to do with the fact that red light will not constrict your eye as much, and therefore you're letting in more light, it's easier to see. If you use blue light or white light, it's going to constrict your eye too much and you'll lose the ability to see that. That's what I would surmise. Okay. All right. Now let's talk about global circulation. And what we're really saying at this point, what we're really asking is, why do we have seasons? And you know the answer to that. What's the answer to that?
Because of the tilt of the earth.
Okay, so the tilt of the earth is why we have seasons. Reviewing, the tilt is 23.5 degrees off of the perpendicular to the plane of the ecliptic. We talked about that in class. Go back and review it if you need to. But that means that sometimes the northern hemisphere is pointed toward the sun, the summer. Sometimes it's pointed away from the sun, the winter. Sometimes it's not pointed toward the sun or away from it, and that's an equinox, so the sun's directly over. So the tilt What are the two things that influence the seasons based on the tilt?
The length of day,
The length of day changes and
the amount of direct sunlight.
the amount of direct sunlight. In other words, sometimes when we're tilted more toward the sun, the sun is most direct. The most direct sunlight is if it's at the zenith at noon. It's right overhead. But when it's coming at the smaller angles off the zenith, that's the more direct sunlight. So the tilt is changing the directness and the length of day. And that's why we have seasonal variability. We have diurnal variability, day-night stuff, because the sun's light is from the horizons coming more overhead and then going back toward the horizons. So we have a variance in the incoming radiation, and that changes the temperature. We have the warmest time of the day, a couple hours after noon, because even though we're getting less intense radiation, we still have more coming in than going out. That controls temperatures. But if I ask you, why do we have weather? What is the answer to that question?
Because
What do we got, Aaron?
she says the rotation of the earth.
No, the rotation of the earth gives us the diurnal variation. What fact about the earth tells us why we have weather? A second grade answer would be this. The poles are cold and the equator is warm. That's the second grade answer. So let's take a look at a second grade answer. And we're going to go really early second grade, and we're going to assume a flat earth. So here's the earth. I'm going to assume this is the ground. And I'm going to assume that this is the North Pole. This is the equator. And this is the South Pole. And so what happens is the sun heats the earth. It's warmer at the equator, colder at the poles. And I'm going to base this on a lie. The lie is this. Write this down. Warm air rises, cold air sinks. Given that, where will the air be rising? Everybody, just where's the air rising based on that lie?
At the equator,
And where will the air be sinking?
at the poles.
At the poles. Okay? Now, I want to show you something. And this is a concept known as mass continuity. This is a foundationally important concept, so we're going to start it, but it's really easy. Now, folks, respond to me quickly. What is the definition of air pressure?
The weight of the air above us.
Okay, so what would the definition of water pressure be?
The weight of the water above us.
Okay, so imagine that I've got a tube, and in the tube, there's water. Okay, do you agree that the pressure on the bottom would be higher because it's the weight of the water above you? Fair enough?
Mhm.
Okay, so let's imagine that I put in a series of holes up top and down below. So I put some holes in there. The only thing is, I am taking water and I'm pumping water into the holes down here. What will happen with the holes up top?
Water would escape.
Okay. Now, These arrows are going like this. There's a word for that. What is that word called? Convergence.
Converging?
What's the opposite of convergence, where they're going apart? Everybody?
Divergence.
Right? Convergence, divergence. Now, what is happening when I put the water in and the water comes out up top? What's it doing inside the tube?
The water's rising.
Isn't the water going to be rising? That is mass continuity. It makes sense. What if I pumped water in the top? What would happen? It would sink, go out. By the way, just a side word, sinking air or sinking anything is a word called subsidence. That's just a word that you need to know. There's nothing special about it. If I said there's subsidence in the atmosphere, you'd say that's sinking air. That's it. Rising air is rising air. Sinking air is called subsidence. It's just a word. Okay, now, mass continuity in words says this. You ready to write? Mass continuity says, when I have a level of convergence in the atmosphere, when I have a level of convergence in the atmosphere, I must also have a level of divergence and vertical motions in between. They're inextricably linked. Have you ever used that word, extricate, to get out of something? Sometimes if somebody was in a car accident, you'd have to extricate them from their car. So inextricable means you can't separate them. They're joined, and they're always joined. So when I have an area of convergence, I also have an area of divergence and vertical motion in between. That's got to be the case. So looking down here, if the air is rising at the equator, what must it be doing aloft? You guys keep your mics off so you can answer. These are simple questions. What's the air doing aloft?
Moving towards the poles.
Well, it's doing what though?
It's diverging.
Right, so it's diverging. And what must it be doing at the surface?
It's converging.
Okay, so it's doing this. Now, this is obviously converging because the world is not flat, so it's coming at it from the other way. So you could do things like this, right? You can think of it this way. Because it's not a flat world. So what I have is I have areas of convergence. Like this, and then areas of divergence are here, right? So I have rising air at the equator and sinking air at the poles. Does that make sense? Okay. This circulation, right? And I want you to think of this as this is a circulation. And in this circulation, air is rising and sinking. Air is rising and sinking. This is what's known as the global habits. Remember, we base base this on a lie that warm air rises and cold air sinks. That is not going to be true. But for now, let's just imagine. And this is kind of what would happen. Now, if you are standing here in the mid-latitudes, according to this, what direction are the winds? Julia, what direction are the winds where I'm at? Is your mic working? I don't hear you either. Don't know to hear you. You and your mics today, that's funny. Isaac, what direction are the winds here?
Looks like they're coming from the west.
Aren't they going this way? Isn't that what I've drawn?
Yeah.
Which way is this? That's the North Pole, that's the equator.
Oh, I was thinking of like northeast, southwest. Then that's coming from the north.
Okay, so Isaac says it's coming from the north, which is how you define a wind. So this would be a north wind. Now, in the mid-latitudes, what direction are the winds generally speaking? And the answer should be westerly. So this is wrong. It's a simplification. It doesn't take into account the Earth's rotation. But it does give me this concept of air circulating because of differences in heating. So I said, why do we have weather? And I gave you a second grade answer. Why do we have weather? And we said, because the poles are cold and the equator is warm. And then we see a better answer showing that there's circulation. I'm taking the air from the warm areas, bringing it to the cold areas, right? Do you agree with this? This is warm air going toward cold. And this is cold air going toward warmth. I'm circulating the air. I'm mixing it up. I'm convecting. These are convection cells because convection is the transfer of heat within a fluid by fluid motions. Now, I want to go beyond second grade and I want to get to a better idea. So why are the poles cold and why is the equator warm?
It's because the equator receives more direct sunlight than the poles do.
And why is that?
It's due to parallel Earth theory and the Earth being a sphere, meaning that
Okay.
as you get higher in latitude,
Believe it or not, right? It's all about the Earth being a sphere. And, you know, we did mention something you just talked about parallel beam radiation, the sun's coming in. So it's coming in at a much lower angle, right, than over here. We've done this. This is a review. So what we say is that the poles don't receive as much what? As the equator.
Insulation.
Doesn't have as much insulation. So what we can say is the Earth is differentially heated. And why is it differentially heated? Because the Earth is a sphere. Now I'm guessing that I probably might like to give an essay question, because remember, this is take home. And all I would do is, why do we have the weather? Explain. Now I'm warning you guys, because I just graded my other severe weather class, and they did okay, but I had students with 20-point questions, and I said, explain. And they gave me like 3 sentences. That is not an essay answer. didn't have diagrams. So if I give you these long essay type things, not just fill in the blank stuff, the long ones, you better write a lot of stuff on here. And always show the teacher what you know by using vocabulary words you've learned in class. That's how you do tests, especially essay tests, especially take-home tests, because you can go and find out everything. So, you know, you're going to use words like insulation, differential heating because it's a sphere. You're going to talk about the directness, parallel beam radiation. All of those things are great. And if you remember that there is this area in the middle, around 43 degrees latitude, that has a deficit north of that, or poleward of that, and a surplus of radiation. And that excess heat is building up, and this excess cold is building up. And so the atmosphere convects, and that convection is the Hadley cell. That's the transfer. But it's wrong because it doesn't take into account the Earth's rotation. So now what happens that we spin the Earth? What happens to this simple model? Well, it breaks down into something different. Before I erase this, does thou havest any question of this? That's my old English. Does, you know, what's your level of understanding on the stuff we've gone through on this screen right now? 1 to 5, show. Okay, I'm getting a lot of 4s. Julia, 3. What do you want to ask about?
Can you hear me? Yeah.
Yes, I can hear you.
So like, can you just go over how, because like the diagram shows it if the Earth was flat. So like, how does it
Okay.
work? Because the
So,
Earth.
yes, I'm not gonna do it too much right now, but let's just take a look at this. The Earth being flat is just so that I can draw these circulations,
Mhm.
right? And we know that the equator is warm. And then I said, we base it on light that warm air rises. It's not really the case, but for now, you're just going to kind of say that. So it's warm at the equator, it goes up. It's cold at the poles, it sinks. Then mass continuity said, well, that completes the circulation. And you know, and then I asked, well, why is it warm at the equator? And then because it's spherical. But if I were to draw this on this, all I'm saying is that the air rises at the equator, goes up this way, sinks, and does that. Right?
Okay.
So that there is this circulation there.
Got it.
That help? Okay, good, good. Any other questions that any of you want to answer? How you doing, Shannon? Everybody okay?
Yeah.
Okie dokie. So let's, now that I can erase this, let's go back. We'll still keep it as a flat Earth. Okay, but this time I'm going to break it down: equator, North Pole, South Pole. But I'm going to go to 30 degrees latitude, 60 degrees latitude, 30 degrees north latitude, 60 degrees north latitude, right? And what I have is I still have the air rising at the equator and sinking at the poles. But when I spin the Earth, what I find happens is I get sinking at 30 degrees and rising at 60. So it looks like this. And then mass continuity says it's going to do this. Now, do you see how easy this is? This isn't really, I don't think this is really hard to kind of see why it's circulating. I mean, you could sit there and go, well, why is it 3 cells like, or, you know, why is it 3 cells per hemisphere? Or why is that? And I'm not going to get into that, but I've got this circulation. So do you see circulation cells that now look like this? Mass continuity says I've got convergence. What color was convergence? White, I think. Convergence, 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 convergence. And then I have divergence, divergence, divergence. Right? Is mass continuity pretty easy to you guys? Does that make sense to you? I think that tube is good. Okay, so I've got this scenario. Now, all I have to do is go, well, this and that are called the tropical Hadley cells. Right, there's two cells here, two circulations. And notice it's in the tropics, between 0 and 30 degrees. That's the tropics. In the mid-latitudes, these cells are called Ferrel cells. And then this one, what do you think that's called? If this is the tropical cells, what are these?
Polar cells.
Polar cell, right? Fair enough? This, how crazy is this? This is called the 3-cell model. 3 cells per hemisphere. Pretty easy, isn't it? Now, where's the warmest? According to this, we know this is the warmest. And then this is, do you agree that 30 degrees is still warm? And then we get cool. And then we get coolest. Does that make sense to you guys? You need to finish drawing that? Go ahead. Okay, everybody good? Now, I want you to look at this right here. Warm air is rising, cooler air is sinking. Which is the warmest in this cell? The warmest air, indicated by cool, is rising, and the coldest air is sinking. But look at the Ferrel cell. What's the warm air doing? Sinking. And the colder air is rising. Remember I said warm air rises, cold air sinks? The Ferrel cell is backwards. The warm air, for its circulation, is sinking, and the cold air is rising. The Ferrel cell, well, here, let me do this. A circulation is called thermally direct or thermally indirect. A thermally direct circulation is one that has warm air rising and cold air, what? Sinking, subsidence. Thermally indirect circulation is just the opposite. Cold air is rising and warm air is sinking. So listen to, are you finished? Listen to what I'm going to say. If I ask you, what is a thermally direct circulation? The answer is warm air rises, cold air sinks. What is a thermally indirect circulation? It's where cold air rises and warm air sinks. Which circulations are thermally direct? What circulations are thermally direct?
Polar and tropic.
The polar cells and the tropical Hadley cell. Would you agree that the global Hadley cell is also thermally direct? What's a thunderstorm? Isn't a thunderstorm warm air rising in the updraft and cold air sinking in the downdraft? So a thunderstorm is thermally direct. Almost everything we talk about is thermally direct except what? The Faro cell, which is thermally indirect. Do you understand what I'm saying? Does this make sense to you? Give me a thumbs up, thumbs down, whatever. Okay, now let's take a look at this. Imagine that you're standing here in the mid-latitudes. According to this diagram, what direction are the winds now?
Suddenly.
They're southerly winds. Okay, they're supposed to be westerly. So this is more correct, but something's missing. And the something that's missing is called the Coriolis force. So
I can't see the whole definition on the screen.
causes moving objects to deflect. That looks really bad, doesn't it? Deflect to the right in the northern hemisphere.
Thank you.
You're welcome. If it deflects to the right in the northern hemisphere, what do you think is true? What do you think is true in the southern hemisphere?
Deflects to the left.
Okay, so I'm not going to write that down, but that's true. And you should know that. Is that your sack?
No, that was.
No, that's our phone.
Is that a phone?
Yes.
How many of you have phones in your house? Well, besides them. Do you guys have phones in your house? Or is your house now totally cellular? A couple of years ago, even though I'm old, I got rid of my phone. I'm like, why do I have two phones? Why am I paying for a phone when I have my cell phone? It was sad. I lost my home phone number. I felt like a part of me was dying. You know what I mean, Kevin, right?
Yeah.
But yeah, I'm cell phone now. Sam, you still got your house phone? Do people ever call you on that, or is it just your folks?
We just use it for like subscriptions and memberships.
I know. I used to use it, and I got only people who called me was the pharmacy and sales, telemarketing. I'm like, screw that. I'm done. So I got rid of my phone. I'm so sad. 469-8377. Those are numbers you never forget. Anyway, everybody has, what was the, by the way, just a quick question. Julia, when did you first get your first cell phone, your smartphone?
Me?
Yeah.
I got my cell phone when I was like 13, I think.
How about you, Ryan?
Probably around the same age, 13, 14, I think 8th grade, 7th grade, maybe.
How about you, Isaac? Anybody get it?
I got a flip phone in 5th grade for personal reasons. Then I got a smartphone in 8th grade.
Well, right. If you don't have a house phone, you got to have some access. Somebody, call, right? Usually it's mom or dad saying, call me if you need something. You know what it was like a long time ago? We used to drive, and this is all before your age. So you have no idea. Kevin, you're going to understand this. Do you remember the years where you used to drive your car and you would go someplace and you just kind of wrote down the directions? And if your car broke down in the middle of nowhere, you were screwed until somebody either stopped or you walked someplace. You couldn't call somebody. You didn't have a map. You just go, ooh, I messed up. I kind of think that's a bad idea right now. I'm happy that all of you in the middle of nowhere can call somebody. I mean, hell, you could live in Madison, Wisconsin and still call somebody. Anyway, sorry, why did I do that? Okay, so is everybody good on this? So the answer, what is this word? Everybody say the word Coriolis.
Coriolis.
Corey, like in somebody's name, Coriolis. Do it again.
Coriolis.
Because a lot of people like Corleone or whatever. Coriolis. So we get it because of the Earth, and it causes moving objects to deflect to the right. Okay, so what I'm going to do is I'm going to show you a little video on the Coriolis effect, and we'll look at a video. I don't know who's good at any of these things. The Met Office has, well, let's look at the Met Office. They're usually pretty good.
Okay, so we know the
It's Australian.
And this spin has implications in the direction of this wind. We call this Coriolis. Now you may have heard of the Coriolis effect or the Coriolis force, but this is not the real force. It's what we call an apparent force. It all depends on your point of view.
Stop. You need to write that down. The Coriolis, and this, okay, so the Coriolis force is something that we're going to get into a lot of detail in the next unit. But I want you to know right now, it's an apparent force, A-P-P-A-R-E-N-T. It appears to be real, but it's not.
No,
Can you guys?
we couldn't hear it.
You couldn't hear it?
We just barely hear this guy.
Really quiet.
Okay, then let's do this. How about this?
Of the wind. We call this Coriolis.
No,
Not better.
Not much.
Hold on. Ah, crap. I didn't mean to do that. Where's the chat room? It's chat. There we go. I'll send it to you. Okay. So if you want to go ahead and just mute me or something and watch it, I'll watch it. But apparent means it appears to be, even though it's not real. Okay. Can you think of another force that appears to be real, but there's really no force?
Aaron says gravity.
No, gravity is very real, right? You can't see it, but gravity is a real force. But you ever been at those when you spin around on the thing and the floor drops out?
Yeah.
English rotor or whatever they call them. Cajun cliffhanger, Great America. You know what I'm talking about? The rides that spin and the floor drops out and you stick to the wall? That's the centrifugal force. There is no centrifugal force. It feels like something's pushing you out, but it's not. That's an apparent force. Okay, so let me go back to sharing the screen. I'm going to watch this video again because I just want to see the rest of it. You'll see.
Coriolis effect or Coriolis force. But this is not a real force. It's what we call an apparent force. It all depends on your point of view, whether you're looking down from above or back close to the ground on the looking from below. Now, this is quite a complicated sounding business, but I've got a simple experiment to show it here. Chopping board, we've got a disc of paper, pins to that chopping board, a ruler, and a pen. I'm also going to need a little bit of assistance, so Helen is joining me, and she's going to spin the disc of paper as if it was the Earth, as if we were looking down from the North Pole, or above the North Pole. That means you need to rotate that disc anti-clockwise. I'm going to draw a straight line along the ruler as Helen rotates that. And just look what happens. The spin of the Earth means that that straight line is not straight. If you were looking from here, you'd see that the winds would be bending round to the right. That is Coriolis in action in the northern hemisphere. If it was the southern hemisphere, we were looking from below the South Pole, we would spin the disc the other way, clockwise. Try that at home, and you will see that the winds bend the other way, to the left. Now, you may have heard that the Coriolis makes the water spin down plug holes in different directions in different hemispheres.
No.
That turns out to actually be a bit of a myth. Plug holes are just too small a scale for Coriolis to really have any impact. But it is the reason why low pressure systems and tropical storms rotate anti-clockwise in the northern hemisphere, but clockwise in the southern hemisphere.
Hey. Oh, that's not Australian. I thought he was Australian. Really good though. You know what? As long as we're here, let's do this too.
The last video showed that different parts of the Earth heat up differently, with the equator receiving more radiative heat from the sun than the poles. And the purpose of global circulation is to redistribute this heat. If the Earth did not rotate and was a simple landmass with no oceans, we would have a single circulatory cell in each hemisphere, where hotter air would rise at the equator and flow toward the poles. The air would sink as it cools and then return towards the equator. But the unequal distribution of land and ocean and the speed of the Earth's rotation make this circulation system more complicated, giving us a three-cell pattern which exists in both the northern and southern hemispheres. The largest cells are the Hadley cells. At the equator, the warmer, less dense air rises. It rises to a height of about 18 kilometers and spreads out underneath the tropopause. The tropopause acts as a lid to the lowest part of our atmosphere, which contains all of our weather. The warm air spreads out towards the poles, gradually cooling and sinking as it moves, before descending to the surface and flowing back to the equator. The smallest cells are the polar cells. Cold, dense air descending in the polar regions flows at low levels to about 60 to 70 degrees north or south. As the air leaves the polar regions, it starts to warm and rise, returning to the poles at high levels. Between the Hadley and polar cells are the feral cells. Unlike the other cells, the feral cells are not driven by temperature. These cells flow in the opposite direction to the Hadley and polar cells, acting like a gear. These circulating cells not only transport heat from the equator to the poles, but also result in semi-permanent areas of high and low pressure due to the rising and descending parts of the circulation cells, giving us our climatic zones. Where air is rising, an area of low pressure is created. So these
Okay, so in other words, where there's low-level convergence, the air is rising and diverging, and that area is going to be lower pressure. The surface air will be less low pressure. So basically, we'll have low pressure around the equator, and we'll have low pressure around 60 degrees of latitude where it's rising. So rising air is low pressure. Now, let's do something really simple. How do we get weather? What do we need to get precipitation? Two things.
Is one of them instability?
It's not instability, because instability can get me thunderstorms. But just precipitation in general, if the air's not unstable, I still can get weather with these two things. They're simple.
Just water,
Okay, well, not water. I need
water vapor.
vapor, right? So I need moisture. And this is simple. What produces precipitation? Simple answer. Stupid question. What produces precipitation?
Clouds.
Okay, clouds, right? What are the two types of precipitating clouds?
Homogeneous and then heterogeneous.
No. Clouds, cloud types. We've done this. What are the two cloud types?
Cumulonimbus.
Cumulonimbus, and that's the unstable one. What's the stable one? Yeah, I think, Lena, you said it, nimbostratus. At least that's what I could read from your lips. Okay, nimbostratus. So the idea is that I can get clouds of either type if I have clouds. Well, how do I get clouds? What does the air have to do?
Doesn't it have to rise?
Okay, so the two things I need for precipitation is moisture and rising air. So when I have this area, of low pressure, I get rising air. So on the globe, where will it be rainy? At the equatorial regions and at 60 degrees latitude. Now, let's see, hold on, let's go on.
Areas see much more rainfall. This is why the largest areas of rainforest are found near the equator, and why the United Kingdom has a relatively wet climate. Where air is descending, an area of high pressure forms.
So subsidence, areas of subsidence is surface pressures that are high. So we get high pressure at 30 degrees latitude and at the poles. Now, well, here, let me see what they say.
Giving largely clear skies and little rainfall, which leads to the desert regions. But not all deserts are hot. Antarctica sits under the descending branch of the polar cell and is also classed as a desert.
Right? It's a desert too. Deserts are basically less than 2 inches of rain a year. And it doesn't precipitate that much at the poles. So it's a desert. Now it's cold, but it's a desert.
With more precipitation falling in the Sahara, Antarctica is the largest and driest desert overall. Check out our video on atmospheric pressure for more on how pressure leads to weather. Our next video shows how the rotation of the Earth gives us jet streams and prevailing winds.
Well, let's do it.
What's going on? Well, it's all to do with the jet stream, as is often the case, the jet stream at the moment.
Talking about the jet stream and its position has become more commonplace in weather broadcasts. It is often blamed for why we get the weather we do. But why are we so interested in it? And how does it influence our weather? A jet stream is another name for fast-flowing currents of air that encircle the globe at high altitudes. The major jet streams are the polar front and subtropical jets. They can reach speeds over 200 miles per hour, but this speed is not constant throughout the length of the jet stream. Embedded within the wave-like pattern of the jet stream are localized areas of very fast winds. These are known as jet streaks. Even though they're relatively small-scale features within the larger jet stream, jet streaks are important as they provide a focus for modifications to surface pressure patterns. Typically, jet streaks.
Here, this stuff, are you hearing it okay, Kevin and Aaron?
Yeah, better.
Okay, you're not going to take notes on this. This is a preview of what's coming, because in order to get to this level, we have to think a lot more. But I want to play it for you anyway.
Forming confluence zones where branches of the larger jet stream merge. This causes the air to speed up, just like the accelerating current of the two meeting rivers. Whilst the air flowing through a jet stream can reach speeds over 200 miles per hour, the jet stream itself only slowly moves downwind. Its position within the trough ridge pattern of the larger jet stream influences the resultant shape, which in turn affects the development of weather at the surface. A strong jet streak on the left or rearward side of a trough will cause that north. This northward component is the ageostrophic wind, which results from the imbalanced forces. In the entrance region of the jet stream,
I'm going to skip this a little bit. Hold on.
Creates an area of upper level convergence. These areas of divergence and convergence have a significant influence on surface pressure and the weather we experience. Diverging air at high levels means that the air in the column is being depleted. To fill this depletion, air from below rises. If this region of diverging winds is stronger,
Stop.
corresponding convergence.
I was just about to do this, so it comes up right. If this region of diverging winds is stronger than the converging winds, does that make sense in this diagram? Then what's true? First of all, what's true on the surface? What's true on the surface? What kind of pressure is on the surface?
Low pressure.
Right, low pressure. Because rising air is associated with low pressure. So if this is true, this sentence, what can you tell me about this area of low pressure? What do you think? What do you think, Ryan?
Is it being lifted up?
No.
Would it be classified as unstable?
We don't know the temperature distribution, so we don't know whether or not it's stable or unstable. What will happen to the strength of this low?
Aaron says weaken.
Do you think it'll weaken everybody else? Do you think Aaron's right? Look, in this tube of water, I'm pumping water out the top and into the bottom. What I'm doing is I'm taking more water out of the tube than I'm putting back in. So what would the water level in the tube do if that were the case?
Decrease.
It would decrease. So what would this low pressure become?
Less.
All right. Do you agree that the pressure would become even less? So Aaron, is that what you were thinking, that the pressure becomes less? But an area of low pressure becoming even lower is a strengthening low pressure. Does that make sense? Low pressure systems that are stronger are even lower. So even though the pressure is decreasing, the low pressure is getting stronger. Yes or no, everybody? Does that make sense?
Makes sense. Yeah.
Okay, good. Let's continue on that. So I thought that was important for you to see that. Good, I can I just want to make sure I don't lose that thing.
Converging surfaces. There is overall loss of air from the vertical column, as pressure is the weight of air in a vertical column. If the amount of air decreases, the surface pressure must fall. This would cause an underlying surface low pressure to deepen, bringing increasing wind speeds and heavier rain. For an underlying area of high pressure, this situation would cause surface pressure to lower, its blocking effect and allowing westward progression of weather systems. For the left entrance region where air is piling up, there is an overall unsettled weather.
Well, here, I guess I can
This
do
would
this.
cause an underlying there is an overall increase in the mass of air in the vertical column, and so surface pressure must rise. This would cause an underlying surface low pressure system to fill and weaken, bringing decreasing wind speeds and less unsettled weather. Pressure in an underlying area of surface high pressure would get even higher, continuing settled conditions, but also increasing the risk of visibility problems caused by haze, mist, or fog. Our journey now takes us to the core of the jet stream, where the Coriolis force has caught up with the increased pressure gradients, and geostrophic balance is restored. However,
We can skip this.
air. Meteorologists look for the right and the three-dimensional nature. And
I think that's good enough. So I really like the Met Office videos that we show, that I can show you. I think they're really well done. That one was a little bit more complex, and it's probably too much. You know, sometimes people who know a lot of stuff don't know how to break it down into simple parts. The first couple of ones were good, but let's go back to this and look at these. So once again, does that make sense to you? So where is there going to be areas of low pressure? Areas of low pressure will be here at the equator, 60 degrees, where there are going to be areas of high pressure, there and there. Right? Now the winds here are south, so I want you to think about something, so pay close attention. If the air is traveling this direction, but it gets turned to the right, which way will the air travel now? The right would be into the board. Can you see that? If it's going this way, like you're traveling to the north and I said, turn right. Which way are you now traveling? How many of you are like directionally challenged human beings? Are you good with directions? I don't know, maybe 30% of my students have no idea what directions anything is. Like you come out of your front door, which way are you facing?
North.
West.
Okay, so some of you know. How the rest are some of you like, I don't know. You're directionally challenged.
Or now I'm facing south.
You're facing south now?
Yep.
That's because you're a severe weather guy. You always face south.
The only directions that matter are everyone but east. So
right. Okay, so if I'm traveling to the north and then I say turn right, I'm now traveling to the east. So the winds are from the west. And there's your westerly winds. So we'll show you how that goes. So now, and this is what Julia was asking about. Julia, you still there? Julia, are you still there? No. Okay, I'm going to get rid of this, okay? And I'm going to draw in a new board. And I'm going to draw this. And I want you to draw a really big circle. And because I have some experience drawing these things, I can draw pretty decent latitude lines. Right? And what I want to do is I want to draw on the Earth, I want to draw that 3-cell model on its sides. Okay, so this is what we're talking about. So I can use it with this color, and I'm going to go air is rising, sinking, rising, sinking. Right? And I can continue the circulations like this. Okay. And because this is a globe, I can draw my, I don't know if I can do this. Yeah, I guess I can. I can draw my latitude lines like this. I guess maybe. Does this work? I don't know. I can't draw the circles I really want to draw. So I'm not going to draw them. But the idea is this, watch this. The air is traveling in the polar regions from the poles to this area. Like that. Remember, we have high pressure here. The air is traveling to the north. It's traveling to the north over here. Right? And then what's it doing in the tropical regions? It's traveling to the south. But that's not the way the wind is actually going, because what does those winds are prior to the Coriolis force. What does the Coriolis force do? It makes the air turn to the right. So what I can do is I'm going to turn to the right. You see how that goes? And those winds are known as the prevailing westerlies. Prevailing, meaning they're not always westerly, but that's what's most common, west winds. What do the winds do here? I want to draw a red arrow that turns to the right. What direction will the winds be?
Here it says easterly.
Easterly. These are known as the polar easterlies. What about here? They turn to the right. Do you understand that that is the right? Because if I'm going south and I turn to the right, I am now headed west. Because the Coriolis force is weaker at the pole, at the tropics, they're not really easterly. They're what we call the northeast trade winds. Does that make sense? Now I'm going to have you draw this stuff on a test. I will not accept my diagrams in lieu of your diagrams. Did you hear what I said? I am going to ask you to draw these things and label them on the test. But you must draw them. You cannot cut and paste. So over here in the southern hemisphere, we need to do the same thing. Oops. And so what we would draw is the 3-cell model. With sinking air like that. You see how really easy this is? If you just think of some basic principles of sinking, rising, sinking. And then you draw in the winds that are moving this way. Like that, like this. And then the actual winds are turned, what way do they turn?
Left.
They turn to the left. And that's the left. If you're headed south, you turn left, you're headed east. So what are the winds in the southern hemisphere in the mid-latitudes? They're still prevailing westerlies. This way they turn to the left. They're still polar easterlies, and here they turn to the left. And what do they become here? They're not the northeast trade winds, but they're now the southeast trade winds. Does that make sense? Now, I want you to see something over here. Imagine that I put a paddle wheel in this region. Which way would this paddle wheel spin? The winds up here are from the west. Winds up here are from this direction. So which way is this air spinning?
Clockwise.
It's spinning clockwise, right? So clockwise is what we call anticyclonic. This area of anticyclonic, we know, is an area of high pressure. Big H here. And so an area of high pressure is what we call an anticyclone. But what happens down here? If I put a paddle wheel here, which way does this paddle wheel spin?
Anti-clockwise.
Right, it would go this way and this way, and so it spins. Except we don't say anti-clockwise, that's British. We say counterclockwise. But it's still an area of high pressure, which means in the southern hemisphere, it's still anticyclonic. Now, The question is, what does that word mean? So here's a word, cyclonic. Cyclonic means same direction the Earth rotates. That's the definition of cyclonic. So what I want you to imagine is that you're looking down at the North Pole. He did this in the video, so if you need to go see it again. And when you're looking at the North Pole, which way does it spin? Counterclockwise. That's cyclonic. If I'm looking up at the Southern Hemisphere, it's still spinning the same way, but I'm looking up at it this way. Which way is it spinning now? Clockwise. Cyclonic. So here, take your right finger, look down at your right finger and make your finger spin counterclockwise. So you're physically going to do this. You're going to look down at your finger and make your finger spin cyclonically, counterclockwise. Now, go up with the same rotation, go up above your head, and now looking up, like you're from the South Pole, which way is your finger spinning now?
Clockwise.
Isn't it spinning clockwise? So this is cyclonic, this is cyclonic. It's the same way. The Earth is spinning cyclonically. But looking down at the North Pole, cyclonic means counterclockwise. Looking up at the South Pole, cyclonic means clockwise. So cyclonic is counterclockwise in the Northern Hemisphere, clockwise in the Southern Hemisphere. And then the opposites are true. So high pressures are always anticyclones. Well, what about this? Look at this, guys. I'm going to make an area of a little paddle wheel here. Which way will that paddle wheel spin? Air is going this way, this way. Do you agree that that paddle wheel spins counterclockwise, which is cyclonic? And that's an area of low pressure. Does that make sense? Now, any questions on this diagram so far? What is this cell? What's this? That's the polar cell. What's this one? Feral. And this is the tropical Hadley cell. Right? You got to know this. Couple things. Where is it raining? It's going to be raining here. So this is wet. And this is wet. Now, you remember, because the air is rising. But we also have what's most of the world at the equator. Here, let me show you something. World map. Here's a world map. We've got the rainforests of Central Africa. We've got the Amazon rainforest. We've got Indonesia. But for the most part, do you see it's almost all water everywhere else? So we have a lot of water and air rises. So we get a lot of rain at the equator. Here's the thing though. This area has really big thunderstorms. These thunderstorms are known as hot towers. Because they go up high. Do you understand that? What do you know about the tropopause? What do you know about the tropopause? Don't all speak at once, one at a time. What do you know about the tropopause?
Is that where the cumulonimbus cloud stops rising?
Well, it stops, you know, it goes at the equilibrium level. It can go into the stratosphere, but yeah, for the most part, right? But what do you know about the height of it? How high is the tropopause? You remember that from Unit 1?
Oh, it's 11 kilometers in height, but
On
then
average, what does it say?
at the equator, it's 15 to 16 kilometers.
So it's really, really high above the equator. It's much lower at the poles. So these thunderstorms go really, really high. What's the average lapse rate of the troposphere? Anybody remember? Aaron, you remember the average lapse rate of the troposphere? I don't, maybe you remember this, maybe you don't. It's on that sheet.
It's 6.5 kilometers.
6.5, well,
Degrees per kilometer.
Degrees Celsius per kilometer, right? So some of the coldest air in the world is up here. That's really, 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 really cold, way up high. But why are these called hot towers? Because water vapor is condensing. Water vapor condenses.
Latent heat.
Latent heat's released, right? So the hot towers are because there's such big thunderstorms with a lot of latent heat. And I'm heating this cold atmosphere, and then this air comes toward this region. Then what does the air do? It sinks. But what happens to air when it sinks? It gets warmer. So the air at 30 degrees latitude is really hot sometimes because it's sinking. Well, what's true about the Earth at 30 degrees latitude? It's mostly desert. We've got the Mongolia, the Tibetan Plateau. We've got the Middle East. We've got the Sahara Desert. We've got the desert southwest and parts of northern Mexico. Southern hemisphere, we have the Kalahari. We have this great sandy desert in Australia. So we've got very dry areas, southern hemisphere around 30 degrees latitude, northern hemisphere 30 degrees latitude. Now, you know where it's not dry at 30 degrees latitude? The Gulf of Mexico, or right here in these Gulf states. And that's because we've got the Gulf of Mexico. So there's a lot of thunderstorms that come in the summertime because of land breeze, sea breezes. If the Gulf of Mexico were a landmass, parts of Texas, Louisiana would be a desert. Because it's water, things are different. But that's why we have the way it is. That's how these things happen. Okay, now, any questions on this before I erase this? How well do you understand this stuff? Give me a rating. Well, I've got more 4s and a couple of 5s. Okay, that makes me happy. So let's do this. I'm going to look at one more picture. I'm going to look at a picture of the general circulation Earth. Okay, and when I go there, I can go to images, and I'm going to find these really cool images. And the ones I like this images. Couple things you need to know about. You need to know that this is an area where the trade winds come together. Do you see that they're converging? This is what's known as the ITCZ. Those hot towers exist at the ITCZ. And ITCZ stands for what? The Intertropical Convergence Zone. And the ITCZ is a lot of thunderstorms. Those are known as hot towers. It's an area of low pressure. Got it? Here they call it the mid-latitude cell. That's stupid. We call it the Ferrel cell. So let's see. I want to see something else. I guess we could use this one. Over here, sometimes this area just north of the equator, you know what that's called? It's called the doldrums. Have you ever heard of that term, the doldrums? I'm down in the doldrums. I'm going to do something I've never done. And then just north of this, where there's high pressure, you know what those are called? Those are called the horse latitudes. Why are they called the horse latitudes? Aaron, do you know this one?
C. But she's spelling something. C. B. O. I. Horse. Y. N. L. Latin.
What did she say?
I don't know. It means N. Horse means north. No.
Here, I tell you what, Aaron. Do you know this story? I'm gonna kind of give that story. So let's see what we can do over here.
Not sure.
Okay, so let's do a little history lesson. We had all sorts of civilizations in North America. Where did most people come from originally? Where did people in this area come from? The indigenous people of the Americas.
From
They
Asia.
came across here from Russia into this area. It wasn't Russia, but what's Russia now? Do you know what this is called? This region here where there's water? Anybody? Have you ever heard of this, the Bering Sea? There was a long time ago, there was evidently a landmass that people from Asia could come across its landmass, and you could come into the North American continent. And evidently people groups did. I'm watching over the holidays, I watched a show on Netflix called Indigenous People of North America. It was a great lecture series. I couldn't believe I liked it. And it was just so interesting. Did you know that there's a really big population center back around 1,000 years ago in Southern Illinois, just north of St. Louis? Anybody know what those areas are called? It was called Cahokia. The Cahokia Mounds. There was like a city of 10,000 people. You didn't know that. And there's all sorts of mounds evidently down here. I didn't know that. I don't know that history. Because these ancient civilizations eventually became tribal, and that's what we know as the American Indians, right? We have tribes, the Cherokee, the Sioux, the Crow, the whatever. And so we kind of get that concept. So we think of this as all indigenous area, but then Europe came over. How did Europe come over? First of all, what year did Europeans start coming over? What year was Columbus?
1492.
Do the rest of you know that? Do you know that? How many of you didn't know that?
I knew it was some sort of like rhyme, but I forgot the rhyme.
In 1492, Columbus sailed the ocean blue. We probably ought to know that. I know in this world we can't have Western civilization. That's a sin, but deal with it. Where did Columbus come from? Where's he from? What country?
Was it
Italy.
Spain?
Columbus is from Italy. Who did he sail for? The queen of what country?
Spain.
Spain. He sailed from Portugal. That's where he set sail. Now, looking at this map, the streams in the ocean, how would Columbus have gotten here? First of all, I'm going to do this for a second. I'm going to go back because I want to show you something interesting. Maybe this is a better way to look at it. So what was Columbus trying to do?
Find a new route to India.
To India, right? Here's India. So how did Columbus get to India? Or how did the Europe trade with India? You see how long of a trip that is? It's a treacherous trip. Now, you've been told, oh yeah, people thought the world was flat. No, they didn't. Do you see how far they're traveling? Do you think they look to the south and they don't see the horizon? They know they're not sailing over it. People knew the world was round. Just so you know, that's a myth. They knew the world was round. And they knew this is how you go from Europe to India to trade. Now they had China that came into India, and sometimes you had China that would come in and you would have some influence of Chinese trade. And what was that called?
Silk Road.
Silk Road, right? So you have this path, but it was opening up. We didn't know the world. We were just starting to map things out back in the Middle Ages. So Columbus says, hey, wait a second. I want to go this way, go around the world and come in this way and go to India. Now, according to this diagram, this looks like a really long trip, doesn't it? So Columbus, what he was wrong, he knew the world was round. He had the wrong idea of how big the world is. He thought the world was smaller. He thought that this trip was shorter than this trip. Make sense? I mean, if you were wrong. So he says, well, look it. I'm just going to convince the queen that we'll baptize people. We'll make her queen subjects. We'll bring riches. And he's going to send out. So to go this way, he's going to take this current along Africa before he picks up the northeast trade winds. Because once you're in the trade winds, now you go to the west. So they knew they had to go south before you went west because that's where the trade winds are. He eventually came across, and then he discovered this landmass. Actually, this landmass, that island. Do you know what those islands are? H?
H-A.
No, not H. Oh yeah, Haiti. Haiti and Dominican Republic. It's what's known as Hispaniola. And that's Haiti and the Dominican Republic. Haiti's very dark, very backwards, a lot of voodoo, poverty, earthquakes, terrible stuff. Dominican Republic. What's famous about the Dominican Republic for us here in the United States? We have a lot of Dominicans doing something here in the U.S.
Playing baseball?
There's a ton of Dominicans. There was a time where I think 90% of the shortstops in the major leagues were Dominicans. It's like the Caribbean's big in baseball, and they're Sammy Sosa, Dominican Republic, right? So anyway, they found this, they called it the New Indies or the West Indies. And then they started going. And then when they would go back, they would pick up the Gulf Stream and come back this way. Notice which way are they looping? they're looping anticyclonically, clockwise, because there's high pressure in the middle of the Atlantic. This is where we go, Sargasso Sea, we saw in the last one. If you look over here, Sargasso Sea, or the Bermuda Triangle, Bermuda High. Sam, you're talking about the big Bermuda High semi-permanent in the summer. So you're coming around the south side of this to go this way. That's what's going on. That's how people knew to sail here. Now, Columbus had no idea that this landmass was there. And most of his sailors said, once you came off of Africa, what do you start losing? What do you run out of? What do you think is going to be the biggest problem? You're surrounded by salt water. Where do people get fresh water? Hopefully where it rains. Where doesn't it rain? In high pressure. So you got no rainfall, you start running out of water. If you were here, you'd go inland and pick up water. So people would find food and supplies all along the coast, and they knew all the places they could port and they could get water and supplies. But when you come here, you don't have that. So Columbus said, well, we're making good progress. And his sailors wanted to mutiny and go back home because they thought, this is stupid, we're all going to die out here. Columbus was a good leader. He was able to convince them. They finally found land over here at Hispaniola. And then you know the rest of the story. But if the Spaniards came out here and got stuck over here, they started bringing horses to the United States or to North America. The Spaniards did. Horses are originally from this area. And then Northern Africa and the Moors, etc. So they started bringing horses. Horses are not indigenous to the United States. Spanish are the ones who brought it over. So prior to Columbus, there were no horses. I mean, we think about horse, like if you think about American Indians, native populations, do you sometimes think horseback? Well, they became excellent horse people. They knew how to control horses better than anybody on earth. Not the Cherokee, but the Comanche. Comanche were known as the greatest horsemen ever to live. They could do, you ever seen those Hollywood movies where they're off the horse and they're shooting? That's what they were like. And they were really hard when you were in battle because they were so good. Anyway, they brought horses over. But when you're coming out here, if you get stuck in high pressure, what do you run out of? Water. And horses have to drink water. They have hay. You're not going to eat hay, but they need water and they need fresh water, and you're drinking the fresh water, and there's not enough for both of us. So what do they do to the horses? They threw them overboard. And that's why they're called the horse latitudes. Because if the boats were out too slow, in high pressure, without good steering currents, without enough water, they got rid of the horses. That's where the name comes from. Obviously, they didn't get rid of all the horses. They eventually made it over. But that's all depends on what the currents and the winds are. And don't forget that the current is reflective of the wind. So we have a lot of currents going this way because we've got those easterly trade winds. When you get up here, you get westerly currents. Here's the Gulf Stream, like the jet stream. So all of these circulations and all of this history of the development of new lands and the growing of the earth as we progressed in boating and all this other stuff, pretty soon we figured this out. Now, actually, some of you should call me. What were the first Europeans to get here? It wasn't the Spaniards.
It was the Vikings.
It was the Vikings up here in Norway. And so what would happen is they would come out here, they found Iceland, and then they found Greenland. And Iceland, when they found it, was really icy. And Greenland on the coast was a lot of forest, even though this is all covered in ice. Greenland's where people live. Iceland's not where people live, or at least much. And then they would come over here and they would land in this area where they call it Newfoundland, Newfoundland, New Finland. And there was actually a time in the global climate where it was actually warmer than normal. They actually found evidences of grapes growing there for vineyards, way, way up north. But of course, we know now that grapes don't do that. They can't grow that far north. The growing season is too short. It was a warm period, a little mini warming period 1,000 years ago. And so you have Leif Erikson, and there's evidences that there's some civilizations. I've heard some weird stuff that there's some Norwegian ancient stuff in Minnesota. It's kind of cool. Don't know what that means, but it's cool. They eventually kind of left and came back, and then the Spaniards came and they settled this area and into Mexico and into South America and into Florida. So our oldest city is actually the oldest city from Europe is Jacksonville or St. Augustine. It's a Spanish city. Actually, the oldest city, this is kind of fun for some of you weather nerds, is there's actually a city up here found by the Spanish before St. Augustine. It was wiped, that was Pensacola. Pensacola was wiped out by a hurricane. The whole colony was destroyed. Then they had to refound it later after Jackson or after St. Augustine. So that's kind of interesting. So this was all Spanish. This whole area was Spanish. And then the English and the Mayflower came in the north side and then down at Plymouth Rock. So this area became all areas of the English and the French, especially up in Canada, mostly English and French. And then, of course, we had the colonies, and then we took over the colonies here, and then we eventually took over Florida. We bought Louisiana Purchase, which was owned by the French, so we got rid of them out. We took over through different wars. We took over the desert Southwest, and that became the United States. And then there was one, who bought Louisiana Purchase? What president?
Andrew Jackson.
No.
It was Jefferson.
Thomas Jefferson. And Thomas Jefferson sent 2 guys and a team to find an inland waterway all the way to the Atlantic for the Northwest Passage to bridge both continents together. Who were those 2 people leading it?
Lewis and Clark.
Lewis and Clark. So if you take a look at the history of the United States, do you see how much influence the global weather patterns have on that type of thing? The Spanish would, of course, come to the south. The English eventually came from the north. Kind of cool, huh?
Mm-hmm.
Okay, so any questions on that stuff? There's one more thing that I want to talk about, and that is these thermally direct circulations. Okay, so what I need to do is I want to imagine that I've got this. So do you have any questions on anything? You're going to have to draw this, but I thought it's kind of cool that you would see that when we look at the history, I mean, 1,000 years, a lot of influences by the climate. Things that happen because of weather and travel routes because of weather. They're called trade winds because they're persistent. But that's where we use trade routes because we knew that we could get there from here. Oh, by the way, one thing I left unsaid. How does Europe go to India today?
To the Panama Canal.
Well, no, the Panama Canal is a good way to get through to go this way.
Oh,
But Europe goes through here, travels the Mediterranean, and goes this way. That's a short route. But what's built there?
That's this. I don't know how to pronounce it, but it's the one that recently got stuck.
Right?
Yeah.
It's the Suez Canal. And that's where that ship got stuck in there. And it was costing like $1 billion a day. Something crazy. Dangerous spot of the world to have a vital canal. A lot of interesting history in the latter half of the 20th century based on what's going on with England and the Suez Canal. If you ever watch The Crown, they do a couple of episodes on this stuff. Kind of cool, isn't it? Isn't history and weather go together really nicely? I think it's pretty cool. Lots of cool stuff that happens. But you got to know your history to know the cool stuff. All right, so we're going back to here. So here is a box. Whoa, that's a really fat box. Here is a box of fluids. The only difference is in this fluid, I'm going to create a partition. I'm going to put a block on this partition. And over here, I'm going to say we have less dense stuff. And over here, we have, whoops, less dense, more dense. And I'm going to define something called the center of mass. You could call it the center of weight, the center of gravity. Have you ever heard of that term? The center of gravity is basically this concept. There is a point in this place that no matter what directions you go from that point, you have half the mass on one side, half the mass on the other side. So where would the center of mass be in this example?
Inside the most dense.
Okay, is it going to be halfway left to right? It's going to be a little bit to the right. What about up and down?
It'd be halfway up and down.
It should be halfway up and down and a little bit to the right. So I would say this is where the center of mass is. Okay? Does that make sense to you? The center of mass is going to define something which we say is called potential energy. All right, now we're starting to circle back to the beginning of the class. What is the formula for potential energy? Here, you guys go look that up and then look up kinetic energy. I need to get some water. You guys find it?
Found kinetic energy's formula in my notes. It's 1/2 times mass times volume squared.
Not volume.
Oh, velocity, sorry.
Velocity squared, okay? What's potential energy? Did you guys find it? What'd you get, Lena? I have no idea what she said. Anybody else here? What'd you get, Isaac?
No, I didn't hear.
No, what is the formula?
I only have kinetic energy. I only have kinetic energy in my notes. I don't have potential energy.
Oh no. MGZ, thank you. That's perfect. I can read that. Mass times gravity times height, MGZ. Okay? So MGZ is mass times gravity. Now, the way that we figure out mass, right? We've got mass of this thing. Do you agree that gravity is pulling things down? But the height is this height. Technically, you would say it's delta Z. So if you really want to talk about it as a height, it's Z or delta Z. I'm not going to get too caught up in that. But this distance from here to the ground, and you got to remember, here's the ground. Okay, there's the ground. That's the distance above that it has potential energy. So we'd say this distance times gravity times the mass, that's its potential energy. Now this thing is at rest, so there's no kinetic energy. So if I took a pen, right? So what I want you to think about is this pen is above the ground. Here's my hand's the ground. Do you agree that it has potential energy? Where do I measure the set? Where is this pen? And actually, it might be better if I did a block. I have a block of something, okay? And the block, when it's on the ground, does this block have potential energy? The center of mass is going to be here in the middle of the block, right? But the block is still above the ground. Now, so it has potential energy, but what's the purpose of potential energy? When I take the pen and I drop it, what do I do? In terms of energy, what am I doing? When what is she saying there, Kevin?
Releasing.
Not releasing. Gets converted. That's the words I want. Potential energy, when I drop something, potential energy is getting converted into kinetic energy. In other words, this pen is above the ground. When I let go of it, there's less potential energy and it's going into kinetic energy. It's moving. So I want you to take a look at this thing. There's no motion. It has potential energy, but how do I convert it over? The first thing that I'm going to do is I'm going to take away, watch, I'm going to take away the partition. When I take away the partition, what's going to happen? Do you agree that the more dense stuff is going to come down and the less dense stuff is going to go up? In other words, oops, this is going to happen. Like vinegar and oil. Now, you could say it mixes for a while, but really, when I release the partition, take a look at this. Show me with your hands what happens to the more dense and the less dense side. Show me what you see happening. Does it just do this? Is this what you imagine?
Like,
okay, so I think Zach's got the idea. Wouldn't it do this? What do you call that motion? That's called sloshing. I think that's what you said, Lena, right? I could look at you and I saw your mouth go slosh. It sloshes back and forth. Like you're carrying a bowl of water and it sloshes back and forth. And if you walk too fast, it sloshes too much and it goes off over the bowl. But eventually it comes to rest, right? If I dropped a ball on the ground, potential is converted to kinetic energy. What happens when the ball hits the ground? What will it do?
bounce.
Won't it bounce for a while? So really what's happening is this, guys. You have Potential converted to kinetic, back to potential, to kinetic, to potential, to kinetic, to potential. Now, eventually the ball comes to rest. Just like this fluid eventually sloshes and it comes to rest. Now, when it comes back to rest, what happened? There's less potential energy. There's no more kinetic energy. Where did the energy go? Energy just can't go away. It must have done something. What did it do? It makes everything a little bit hotter. The molecules move faster. So if I have a ball hitting the ground, then what I'm basically doing is I'm going to make the ball and the ground a little bit warmer. You actually, when a ball hits the ground, you actually hear it. So that's moving air molecules. So they're using the energy to move sound. So sound and heat are two ways of getting rid of that energy. If I had an asteroid hit the ground, do you agree that's moving really, really, really fast? Eventually it's going to hit the ground and come to rest. No more potential energy. The kinetic energy is gone. What happened to it? It got really hot and it exploded. Everything melted. So I'm now going to let this thing move. Now what happens with the center of mass? Where's the center of mass now? Eventually it's going to be the less dense up here and the more dense down there. So where will the center of mass be? The center of mass will now be on the center line. But where will it be up and down?
Towards the more dense.
It'll be a little bit on the bottom. So the center of mass is now here. So do you see that the center of mass moves to the left, which doesn't do anything, but the center of mass moves down. And it's the lowering of the center of mass that converts potential into kinetic energy. So write that down. It's the lowering of the center of mass that converts potential to kinetic energy. That make sense? Now, when the center of mass is here, is there potential energy? Yes, because it's still above the ground. But can I make it go any lower? Remember, it's the lowering of center of mass that converts potential to kinetic. When the center of mass, when it comes to rest, do you understand I can't make it go lower? So I have no more potential energy that can be used or converted to kinetic. So instead of just calling it PE, we call it APE, which stands for available potential energy. Available potential energy is how much is available to be used to convert to kinetic energy. It's crazy. Have you ever heard of anything so crazy as available potential energy? You ever heard that before? Really? You've never heard of available potential energy before? Haven't we talked about this? What's CAPE? Convective available potential energy. It's how much energy is available to convert into kinetic energy. Remember that a thunderstorm uses CAPE to make the air go up. So I'm using convective available potential energy to make the air go up in the updraft. This is all about air coming down. But now look, do you see what has happened is I had something that was less dense move up, something that's more dense move down. Did you hear what I said? The less dense stuff moved up, the more dense stuff moved down. In other words, what kind in the atmosphere, what do we call less dense air? Warm air. What do we call more dense air? Cold air. So what's rising? Warm air. What's sinking? What is that I've described? What is that?
That is thermally direct.
That is a thermally direct circulation. So I sat on a test, and I'm going to ask you this. What is a thermally direct circulation? And the answer is, it's where warm air rises and cold air sinks. Right? That's what it is. What does a thermally direct circulation do? And the answer is, it converts potential energy into kinetic energy. By doing what?
By lowering the center of
By
mass.
lowering the center of mass. So do you understand that all of our thermally direct circulations are converting potential energy into kinetic energy? Now, go ahead and finish writing this. I'm going to show you something. You ready? Imagine that I've got that partition, and rather than removing it, what if I turn it the other way? What if I moved it and I put the cold air up and the warm air came down? What if I actually did that? What would happen? Where would the center of mass go?
It would go up.
When the center of mass go higher up? And what would that do to the amount of potential energy?
Increase.
It would make it more, right?
Increase it.
So, but what did I have to do? I had to provide the motion to make it go up. So what does a thermally indirect circulation do?
It turns kinetic energy into potential energy.
It turns kinetic energy into potential energy. Cold air sinks, cold air rises, warm air sinks, converts kinetic into potential. So I need to have kinetic energy first. And the ferrule cell feeds on the jet stream, which is a lot of kinetic energy. It uses that kinetic energy to help move the air up. I'm not too worried about that, but that's what you need to know. But you ready? Are you ready for the coolest thing ever? This is the fun part. This is where I get like, this is so cool. Where's the center of mass of the atmosphere?
The center of the earth.
Ryan says the center of the earth. First of all, on this stuff, give me a 1 to 5.
Understand it?
Yeah, it's hard to know if you're going to do well in this test because you keep giving me 4s, which is, if I'm talking to you and you're telling me I understood that at a 4, that's great. I'm happy. I hope you do. I mean, I want you to do well on the test. Remember, what happens on the test, guys, most of the time is your essays, your short answers, you're not taking enough time to go study. You're not finding enough information to put it in there. You need to write more about it, okay? That's your biggest problem. That's students' biggest problems, because you need to show me your level 3. Okay? So let's do this. Ryan, you are thinking this way. You are thinking that's the Earth and that's the atmosphere, right? And you're saying the center of mass of the atmosphere is at the center of the Earth. That's what you're thinking, isn't it?
Yes.
But the Earth is not moving. The atmosphere is moving around the Earth. So really, it's best to think of the atmosphere as this. As a big box of air on the Earth. So where's the center of mass of the atmosphere?
In the center of that box.
No, because why isn't it in the center of the box? What's the density of the atmosphere look like?
Dense near the surface and then not scatters, but
Right? Isn't it less dense the higher up you go? Doesn't density decrease? And how does it decrease? It decreases exponentially. So what I have to do is I need to find an area that's half of the mass. Well, I've got to find a point where half of the mass is below me and half of the mass is above me. But wait a second. When I'm standing on the ground, how much air is above me?
all of it.
All of it. And how much is all of the, what do you call the weight of the air above you?
Air pressure.
And what is the standard sea level pressure? What's it on average? Mean sea level pressure. Shannon, do you know? Anyone? Sam, you ought to know this. This number ought to be drilled into your head.
I know it. I know it. I just can't remember it right off the bat. I was thinking that, but I was like,
1013.25 millibars. That's the exact number. We did this before. Say yes, Paul, we did this before. But do you agree that's about how much? It's about 1,000. So where's the center of the mass of the atmosphere? $500 millibars. Right? There's the center of mass of the atmosphere. Now, what do I want to give it? I want to give the atmosphere more potential energy. How do I do that? How do I give the atmosphere more potential energy? What do I have to do? Lena, I wish I knew what you were saying.
like, you mean more available potential energy or potential energy?
Both, same thing in this case. In order to get more potential energy, what do I need to do?
You would move up the center of mass.
I would need to move the center of mass higher up. There's half the atmosphere in this little yellow box. What do I do to make that top of the box go higher? Heat it. If I heat this box of air, what happens when you heat a box of air?
Rises.
Well, no, it doesn't rise. When I heat gas, it expands. You remember the first big thing we did in class? When you heat a gas, it expands. So if I heat this box, then the box gets larger and the center of mass goes up, and I'm getting more potential energy. How do we heat this air? What heats the air ultimately?
Sunlight.
The sun, right? But how does the sun heat the atmosphere? Does it just heat the air and make it warmer? No. The sun heats the ground. The ground can radiate, heat the air, conduction or convection, with latent heat. That's how we're heating the ground. So we heat the air indirectly. It's not the sun as much heating the atmosphere. It's the sun heats the earth. The earth radiates and heats the atmosphere, and it makes the atmosphere warmer. But ultimately, who's doing this? The sun. But what does the sun do to the earth? It heats it. It gives us energy, because what it does is it gives it potential energy. When the earth has potential energy, if I can lower the center of mass, I convert potential energy into kinetic energy. That's done through thermally direct circulations like the Hadley cell and the polar cell and thunderstorms and cyclones and hurricanes. All of those things are converting potential to kinetic energy. And what does the atmosphere do? It starts moving. And when the atmosphere is moving and I've got variable air going up and down, that's what we call weather. That's how we get weather. Now, come on, that's kind of cool, isn't it? When you think about this.
I think that's cool.
The sun heats the air. I mean, how does the sun heat the atmosphere? The sun heats the ground. The ground absorbs temperature, gets warmer, it gives off outgoing long-wave radiation. That long-wave radiation is absorbed by the atmosphere. It also conducts heat from the ground to the atmosphere. It also evaporates water, which is released in latent heat in the atmosphere. All of these things are doing to lift the 500 millibar area, lift the center of mass. Now the atmosphere's got potential energy. If I can convert that potential energy into kinetic energy, the air is moving. Well, the movement comes through thermally direct circulations. But like, what stops a ball from bouncing forever?
Gravity.
No.
Friction.
Gravity. Friction. Resistance. The atmosphere has resistance to flow too. It's friction, or what we call viscosity. So the atmosphere would eventually, if we turned off the sun, what would the atmosphere do fairly quickly? Like 2 weeks. It would stop moving. There'd be no more kinetic energy. And the sun wouldn't be able to give us any more potential energy. We'd have no available potential energy, and the atmosphere would stop moving. And we wouldn't have weather, and everybody would die. Not to consider it'd be damn cold because we turned off the sun. Which is why one of the things that bothers me is, who turned off the sun? Right? You never hear God saying, why did you leave the sun on? God left the sun on. Your mom or dad may say, why did you leave the lights on? Well, you turn the lights off because that's wasting energy. But God doesn't say that. Here's the sun, boom. Because the sun is what's generating and running the weather. And the weather is able to get better and to get differences in circulation because it's a sphere. It's differentially heated because it's a sphere. And that differences of heat creates circulation cells. And circulation cells are generated by potential being converted to kinetic. Kinetic energy eventually stops because of friction. So we have to keep the sun going to give us potential energy. That's how the world works. That's really simple stuff, isn't it? I mean, it's kind of cool, isn't it, Lena? You kind of dig this stuff, don't you? Lena's taken 2 classes and it's like all of this stuff is starting to come together now. Finally, she's like, whoa, I can see the big picture. Right, Sam? How are the rest of you guys? Do you understand the weather here? 1 to 5, give me a number.
Let me see.
What are you at, Aaron?
About
Ryan's going 4. You Ryan 3, 4? What's Shannon at? She's at a 4. Okay, beautiful. So that, mon frère, is this section in the class. And that ends our section, and that's what the test will be over. You think that there might be some stuff from today's lecture on the test? Ryan's got a little celebration inside there, just a bit. I think a lot of the stuff from today is going to be covered on the test because you see where we've gone. We've gone from heated gas that expands to this point, and it's been one big path where we've gotten here. Now the air starts moving. Now we have weather. Now we have to understand how weather actually works. What are the details of weather? So that's why I like this last unit. It's more the physics of forces and stuff. So we're going to kind of go into a completely separate section, but it'll be fun. I like this one. I think this one's where you start putting it all together. Any questions? So as soon as I make the test up on Friday, I will make it available. It'll be available from Friday through Monday night at midnight. So anytime in those 3.5 days, you'll have the opportunity to take the test. I will try to get the essay portion first. I would recommend that you do the essay portion because it forces you to focus on things, get that done, and then take the timed short answer, multiple choice stuff. Are we good? How you
Yeah.
doing, Aaron? Give me a
Doing
smile.
Doing okay.
The rest of you guys, sit, relax, enjoy. A drink by our fire. Is that your house, Sam?
Yeah, I'm sitting out on my porch right now.
Is it nice out there?
Yeah, a little windy though, but
It's still better than being cooped up in your house. How you gonna do, Julia? Oh, where did she go? I said her name and she disappeared. That's pretty cool. I might have to do that to all of you. If you got no other questions, I'm gonna make you all disappear. All right, have a good one, guys. We'll see you on Tuesday. Good luck with the test. If you have a problem, email me. Bye.
hey,
All right.